Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on stream. We have some more lighting work to do today. Uh, Yesterday we finished changing it so that you sent light boxes directly down to the lighting system, and it blew them out into surfaces for lighting, and that appears to be working properly now. So if we run the game, we are getting the standard lighting, the slow lighting, running now with light boxes communicated directly to the lighting system. What we want to do today is to now change it so that when we do our lighting computations, rather than doing our lighting computations on surfaces at all, we're going to do our lighting computation on actual boxes. So as we go, right, at the moment what's happening is these boxes are getting computed down getting transmitted down to the lighting system as boxes, but then they still get broken out into flat polygons for the lighting system. And what I want to do now is change it so that instead of doing that, they actually get changed over to being hit tested against as actual boxes, never getting blown out into surfaces at all. This is mostly a bookkeeping change, but there is one algorithmic change we have to make. And that algorithmic change is we need to do our raycast checking against an actual an actual axis aligned bounding box, which is to say that we have a more complicated task to do than we would have if all we were doing was testing against a single polygon. Now, what we can do at first is change the raycast to just be 6 raycasts, one against each of the faces, but we can quickly make that faster by only using faces that are that are front facing to the ray, and then we can probably do even better than that by maybe doing intersection testing that's directly against the box instead of against the pieces of the box, and so on. So we have a lot of options here that we can pursue, and that's basically what we want to start doing now in an attempt to get this down to something nice and concise, and that we can start using to do multi-resolution work, which is sort of the end goal of switching to the boxes in the first place. Although, in general, even if we weren't switching to multi-resolution, it would still be a much better idea to do raycasting against the boxes, because the raycasting itself would just be faster. So this change is good no matter what we were doing, if you know that you're not taking advantage of the ability to specify polygons by actually using lots of things that aren't directly related to a box, then, whatever. But since we are only ever really concerned with boxes here, at that point, it really makes no sense whatsoever not to just have the lighting system work on them directly, because it will always be able to get a speed improvement based on that. So what I want to do now is, I guess, just do the literal translation of this. So here in the lighting test function, right here is where we blow out the box surfaces, and all I really need to do here is just move this into this part right here that goes over the box surfaces. All I really need to do is move that over into the actual raycasting test. So if you take a look at the raycasting test, the raycast test goes over these source indices here. And so what I want to do is right inside where we decide that this is one of the boxes that we're going to test, what I want to do is just move this this thing right here that does the actual raycast. I just want to move the part that generates the box surfaces right above that. And what I can do is literally take this lighting surface information here, and instead of having the lighting surface be something that's actually stored, I can just make a temporary lighting surface like so, and create that lighting surface on demand. Now, obviously, this is pretty slow, right? We're doing a ton of work here for no real reason, because a lot of this information we don't actually need. And, there's all sorts of reasons why we don't really want to do it like this in the end. But again, when you're making code changes like this that involve a lot of bookkeeping and a lot of information, it usually benefits you to make them slowly, one step at a time, to reduce your debugging, especially in things like lighting where the results can be complicated to interpret. It's a lot easier to do slow changes and make sure that they're working okay, rather than make some giant changes and then spend a ton of time trying to debug why you're getting a black screen and so on. Okay, So this is what we effectively want to do now, and we'll take a look at that in a second. But what we want to do first is get rid of the code that was actually doing any of the blowing out here. So this stuff can all basically go away, right? So we don't really need any of this. What we're going to do instead is change the solution to have the box count specified in it directly. And similarly, it will also will have the boxes. Oops. Specified in it directly. So then when we go back to the lighting solution, oops, that's in world mode still. Not a great place for it, but yeah, we'll fix that someday. These surfaces here that used to be here, these are going to go away, and these are just going to be replaced with light box, box count. There we go. So we're no longer going to be having our own surfaces in here. We're never really going to have that. Instead, what we're going to have is just the light boxes in here that can be directly accessed. And these can just be a pointer. We're not storing them, that it can just point to the one that we were getting before. So now when we come back through here, right, we're going to be able to go, okay, let's just go through the boxes themselves, and we'll do each of these surfaces, and that'll be fine. We'll have to fix some bugs in there, but otherwise it should be good. And also this, right, comes from the solution now. All right. So the source index thing here was only really getting used as well for the, the result index sort of stuff. So what we want to do here is this piece of information that flows out is now going to have to be a little bit more complicated, right? Because once we do our raycast, we're going to need to give some of this, the relevant part of this information, we're going to need to give to the routine that actually has to process this intersection on the way out. So if we take a look at what happens here, you can see we have like these ray indices. We're looping over here. We're doing the sampling and whatnot. And what happens is once we get that closest point index, right, we've got the hit surface, which is this piece of information that I'm talking about that gets returned from the ray. Which surface got hit? That hit surface needs to be used in a couple different places, right? So we need some way of taking care of the hit surface in a way that doesn't require returning an index to a surface that we don't have. Now, in order to do that, I'm going to have to think through what we actually use. So in accumulate sample, you can see that the lighting surface here is getting passed. When we look at the reason that it's getting passed, the only thing it actually needs is the surface normal for the angular fall off. Okay. So that surface normal is actually also present in the point itself, right? Points themselves have their surface normals included in them, and so we could just use that directly. So when we actually come through here and we're passing the hit surface, we don't really have to do that. What we could do instead is just take whatever the hit point was and pass its normal, right? This part here could be that. And if we take a look, oops. If we take a look at what's happening here, let me give us a little more room. We're kind of getting, there we go. So closest point index is the actual thing that we would need to get that piece of information out. So if we wanted to say solution points closest point index dot end, that would give us that normal that we actually need. So it turns out for accumulate sample, we really don't need the surface, so that's a good thing. So the only place we're really using the hit surface, the only place that we're really using the hit surface, which is the thing we would need that index for, is this part right here where we loop over the lights themselves. So what we could do instead is just have it so that this index that comes back could just be array. It could be something that just tells us what the point count is, right? So just be whatever the first point index is. We start with that, assuming that it's within range. Then when we come through here, we're going to loop over ray.pointCount, right? Ray first point index. And that would be it. That would be all we'd have to do. So in order to make this routine continue working the way it was working, again, not necessarily the most efficient way to do things yet. We're going to have to start paring this down as we try to make it more and more efficient, certainly. But we can start to see how this routine could still communicate the same information back that was actually necessary. So what we would have here is a first point index and a point count, like so. And when we've got those pieces of information flowing back, what we would need to do is just set them here. So in the result first point index and the result point count, what we need to specify is these two pieces of information here. There's that light index and there's that light count. So those are the pieces of information that we would actually need to pass back to do the iteration on the outside that needs to get done. And similarly, when we initialize this, instead of setting it to the surface count, we're just setting it to the point count. So now at the end here, remember we don't have surfaces anymore, so anywhere that was referring to surfaces has to be changed to box. There's two places where that has to occur. Actually, there's more than two. So there's here where we need to loop over the boxes, which now we will do. And I guess we can still use source index for this. So as we're going over the boxes, we need to do that. But then the other place we need to do it in the immediate vicinity is when we're looping over the emissions. Oh, no, I guess we don't. That's not true. Never mind. So there is really only one other place that we have to loop over it, I guess, and that's in output. So here we were going over the surfaces, and we don't want to go over the surfaces anymore. We need to go over the box count. So this right here is basically a box index. Oops. So the box index that comes out is also going to have to, again, loop over each of the faces of this thing, then loop over the points of those faces. Again, not really a huge problem because we have the ability to generate those on demand, so we can just do that and be done with it, right? This right here is the code that will do that, and we only really need a very little bit of that code anyway. So in here, when we do this and get the box surface, the only things we're using it for is the x-axis and y-axis, so this actually doesn't really have to happen where we translate the thing out. All we really need is these two pieces of information here so that we can go, okay, here's the light index, right? And furthermore, we don't even need to do this addition because we can just read out what that actual maximum value was to begin with and just skip the subtraction, which gives us exactly what we would have wanted. Then inside this call where we go to get the x-axis, y-axis, that can be read directly out of the box surface itself. So again, just we end up in a situation where most of the work we were doing can collapse down pretty easily into something that just operates directly on generated surfaces rather than stored surfaces, and there's no real issue here. Oops. So let's go ahead and clean it up. Where is that point count? Okay. All right. So this is actually boxes, not light boxes. This is not source, it is surface. Oh, actually, I disagree. It is source. Go ahead and change that. And all of these that are doing source arrow need to be source dot. There we go. And oops, a little overzealous there. Actually, I suppose, why not? So the box surface index, yeah. lighting surface does not have member operator. You're correct, it doesn't. There we go. And so did we actually even use that information, that hidden index? No, no, no. So this is points. This is not even, we're not even getting that information. So we don't even care about that anymore. No object, what is the question? Point count, commands light point count. So is this a U32 in here, I guess? And that is not something we actually want to print. Light boxes are just boxes. All right. So now, effectively, we've changed the code over to doing, to doing exactly what it's doing. So what we're doing now is we're going through and we're blowing these things out just when we need them. As you can see, not particularly fast. So we're going to have to go through and now make this a little bit more sane with how it's working. I can also probably do a little bit of work to sort of make sure we're to make sure we know where our timings are being spent, I guess is what I would say. So you can see we're still compiling in O2, so we would expect to have reasonable optimizations here, but there's a bunch of stuff that's going pretty slowly, and the question is, well, why? And so we don't necessarily know exactly, but one would assume that the blowing out, doing this every time, there's just too much actual work in generating these box sources from the indices and that sort of stuff. One would just assume that that is the majority of the problem there. But since we don't really know that, I'd like to go ahead and actually time it to make sure that this routine is where all of our time is being spent. Just to make sure I didn't accidentally introduce something crazier here where I, made some mistake that causes us to do like way more iterations or something like this, because I want to make sure that the thing that's taking the time is the thing that I was expecting to take the time, and not something else, right? Okay. So what I want to do here is just do a timed function so that it'll thought we had one of those. Oops, yeah, gotta put a, there we go. So I'm just gonna put a timed function in there. And so hopefully what'll happen now is every time we go to do a raycast, it'll get counted in the profiler. So if I need to go in now and just verify what is actually happening, I can verify that all the time's being spent in the raycast. It is, so that's great. And so what we really just need to do is focus on making sure that we can hit test against these boxes in some efficient fashion. The number of rays being cast here is not unusually high. 30,000 rays seems reasonable for the number of iterations and number of surfaces and stuff we have. I'm not verifying it in any particular way in my head or anything. I'm just saying that's not unusually high. If that had come back as like 1 million or something, I would have suspected that I made an accidental iteration change somewhere else. So our goal here is just to drive down this function that's doing all of the work. And it was definitely running faster before, so the question is, how do we make it run back at that normal speed, right? Okay. So let's talk about how we can go about doing this. A few things we can do, and so on. So the very first thing that we can do is we can use half the surfaces, right? Let me go ahead and load up Milton here. It is day 422, right? Did I get that right? Yes, just want to double check. Sometimes I forget. All right. So for raycasting against boxes, or in this case, let's just say AABBs, so axis-aligned bounding boxes, what we want to think about first is just the obvious fact that, let's just draw it in 2D because it's a little bit simpler and doesn't really change the principle, that whatever direction the ray is coming from, we know that ray only is going to intersect front faces, right? So if the ray is pointing in this direction, it's never going to be tested against things that are pointing in the same direction as the ray is going, because we don't allow raycasting from inside of the cube, right? Or the box. We only allow raycasting from outside the box, and when we are going from outside the box, we only want to intersect faces that could bounce us off, right? So the first thing we could do is we can eliminate half of the faces pretty much immediately. So if we take a look at how much time is being spent in here, inside the profiler, you can see that it's pretty huge, right? I don't even know. We should probably put some commas in here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's like a billion cycles, right? And hey, isn't that nice? This is a 4 gigahertz processor, I think, and a billion cycles, and our amount of time is around 1/4 of a second. So hey, that works out just about correct. Anyway, so we're taking about 1 billion cycles to do that here, so we should expect to see maybe that number drop, not in half, but it should be something fairly significant if we were to just test that. Now, that's not going to get us even close to where we want to be, because we want to be, if anything, faster than the old version, and that's not going to get us even in the ballpark. So this is by no means the majority of the change we want to make, but we should still be able to say, hey, only test those particular boxes. I guess this is too late to do it. This test right here is the test for that. But what we want to be able to do is we want to be able to do that earlier, right? So here in the box source call, where we're getting this information out for the box surface, what we want to do is we want to test before we ever generate all of this information. And we can do that because we know the sign of the ray direction is going to be the thing that gives us all of the information we actually need, right? Because this is axis aligned, whatever my ray direction is, what I know is that the instant I would need to start testing, say, the y positive, right? That's y positive, this is y negative. The instant I would have to start testing the y positive plane is precisely when my ray direction has a negative y, right? So I don't really need to generate any of the information. I don't even need to do this test because I know these are boxes, I know they're axis aligned, and so at that point I can just make the assumption that the sign of the components of the normal, the ray normal, are all I really need to figure out whether I'm going to test this box surface or not, right? So what I can say ahead of time is, rather than doing the ray source end test, and of course I still need to compute the inner product because you can see here that the inner product is used for a piece of information. But I can pretty much say, okay, this can become an assertion that doesn't actually predicate anything because I pretty much know that it's always going to be true. What I can do instead is do an if statement here that will test the sign of the thing that I actually care about, which is to say the axis index, which again is the box surface index shifted down by 1, right? That's the axis index. Whatever the axis index is, like so, and we know the positive, right? So we know that we have the axis index, which is this, and we have the positive yes or no, which is this. we know that our test for whether or not this thing ever needs to enter this routine is just going to be, all right, if the box, if the axis that I'm testing, right, if the ray normal, what I'm going to be shooting, so the ray direction, if the element of that is greater than 0, that lets me know that I'm testing the negative, right? If it's less than 0, that means I'm testing the positive. So I can do something that tells me whether my normal is positive, which is this, and I can do something that tells me whether my ray is positive, right, which is this, and I guess, you know, test against positive is really what this is, because this is saying whether the ray is negative, right? So if I want to test against positive, and this is positive, then I should do it. Otherwise, I shouldn't. Does that make sense? So all I'm doing is seeing whether or not the signs of these things line up. And I should be able to, after debugging it, make sure that that always is true. Now, this assertion should catch cases where it's not. So to get the code, okay. Hold on a second. As we go through and step through this here, we got to kind of get this. There we go. So what we need to do is make it so this actually does work correctly. Let's just double check what's going on here, because this could also just be a threshold problem as well. Oh, we've just got the assertion backwards. I was going to say that seems like plenty of tolerance. And so what we really want here is that. There we go. All right, so what we want to do here is make sure that we're always It's a slow morning. Let me say that again. What we want to do here is make sure that the inner product is sufficiently negative. So the tolerance is going to swap directions, if that makes sense. We want the ray source normal. We want to assert that it is negative. Now this is probably too much tolerance here. I don't know, but I'm just guessing that it should probably be something lower than that. We'll find out in a second. But I'm pretty sure that that is what should be happening. Of course, I'm not seeing anything, so that's bad. Just in case anyone was wondering. What is going on? Okay. Oh. I'm like, why is it so slow? Because I didn't change back to retail. There we go. So now we're only testing a third of the faces, and we're not doing all of the work necessary to generate those faces. And so now we can see that hey, that number did actually drop roughly in half. And that's exactly what we expected, and it's exactly what we got, right? So that's pretty happy, but like I was saying, we're not really even close yet to where we need to be in terms of getting this to be fast enough. So that's great. You know, we're happy campers. We can remove our assertion because now we're only doing stuff that we would expect to be doing, right? And that's good. Now, what we want to do as well is start to break out what we actually need out of the box source and what we don't need, right? So what you can see here is we need the width and the height, right? So we need these values for sure. we need these values, but we only actually need them in this case, right? So we don't need to actually pull these out unless we're getting to this point. Right, this is the only time we actually need this information. So we can avoid ever actually doing that sort of pull out until here. Now, the compiler was probably smart enough to do that for us, but we don't really want to stress the compiler any more than we have to on a critical path like this. We want to do as much work as we can for it to give it the simplest possible thing to optimize, just so it has the best chance of doing a good job. In this stuff here, you can see that we do a 2.0 times these and then check against the width. So rather than doing that, what we could easily do here is just stop doing this redundant work since we have the half width, right? So now we don't really need any of that in there. For the x-axis and y-axis, obviously these are, there we go. Obviously these are done directly here, so we're not really doing anything here other than just renaming some variables, but I'm just going to make it clear which ones we're doing here, like so. Transparency isn't necessary. The box source P, oops, and N are here, and here, and so now at least we can see a little bit clearer what's going on. All right. So we just cleaned up some of the business there. Shouldn't have really sped up the code at all, and hey, it didn't. So again, like those are all things the compiler could have done for us, so it looks roughly the same. So now what we're going to do is weld this routine in here. So the getBox surface call, which does, you know, a tremendous amount of work here. I'm just going to grab this out directly, and we're going to start to work with it. Here we go. We're going to start to work with it in a more specific way. Where's my Raycast? There it is. So if we drop this in here, instead of calling the function, let's start by just taking that exactly as it is. I'll call this box source. Okay, so we got a couple things we need to do. This needs to be box min corner. Well, I guess we need to like pull these out first, right? All right. So now we should be able to run this directly now and still get the same lighting, which we do. And if you take a look at what happened is just, we didn't do anything, right? I mean, we did literally nothing. That doubled the speed of the function, right? So again, now we're starting to get down, we're about 2x away again from where we were before, which is weird, right? But all we did was drop it in there, and now that the compiler can see it better or some other nonsense, who knows, we suddenly get much faster, right? So, okay, that's good news. Let's go ahead and push this a little further, though. So if you take a look at what's happening here, There's some stuff right off the bat that we can do. Let's first of all, before I go, I guess, any further, let's just see about whether all the things that we're using are actually necessary and whether or not we could be doing something smarter here, because obviously there's possibilities for improvement, certainly. Tons of possibilities for improvements, but let's take some of the simpler ones. So for starters, let me just rename these variables so that we're not accessing off of a box source for any particular reason, right? Here we go. All right, so now we're not like putting them into a structure and taking them out. Now again, shouldn't change anything because the compiler should be smart enough to have done that, and it did. But again, remember, putting that function in there inline should have been something the compiler was smart enough to do and didn't. So you can't always assume that the compiler is going to do something because compilers are very complicated and optimization is a difficult problem, especially for a language like C. So it's important to, actually make each individual change carefully and test to make sure that you can't get that you don't get speed ups when you change things, because a lot of times maybe something that you're not thinking of is preventing the compiler from doing an optimization that it should be able to do, or that you think it might be able to do. So you don't really want to make those assumptions. Anyway, so let's now start making some structural changes to this. If you look at what I'm doing here, I'm looping over the box services, and then I'm seeing whether or not I'm going to test against them by seeing whether they're equivalent, whether the direction is equivalent. The question is, why bother, right? Why not just loop over the three axes directly, like so? And if I have the ability to generate any of the surfaces I want, which I did, why not just loop over the three axes and say, which did you want me to do, right? You want me to test against this one? Great, that's the one I'm going to test against. Forget the if statement. Just, I know I'm only going to test one of the faces for each axis. I'm only going to test one. Let's just pull out which one it is. It's going to be whichever one is positive there, right? So we can get rid of some of the business that's happening there in a pretty straightforward way. And the only thing we have to do now is actually be able to reconstruct this box surface index so that I can pull the light indices out as necessary, right? Actually, that's not even true because we already have it right here. So even that's not true. Wait. No, that is true. So the box surface index, I have to pull out which one of these we're talking about. So in order to create the box surface index here, I just need to be able to take whatever my axis index was, right, and add whether I was positive. That's all I need to do there. So really I could put that up here because that's just something that we just know. As soon as we compute whether or not it's positive, we know what the box surface index is as well. All right. So again, running it. And what we can see now is we're really getting down to the same speed that we were beforehand. In fact, I think now we might even be a little bit faster than we were originally. Oh, but of course we're not actually working. Well, that could be why. Yeah, it turns out if you don't actually work, you get faster. So let's debug that for a second. I need to figure out whether or not I'm trying to test against the positive surface, and so or the negative surface. So what I'm doing here is I'm checking which direction the ray goes for this particular axis index. I feel like that should have been correct. Trying to take a look at now why that wasn't correct. Let me just back this up a bit here. let me just make sure that that was the change. Yeah, there we go. So let's just take that a little bit slower here, because obviously I was going a little bit too fast apparently. So what we want to do now is let's loop over the axes and generate the box index that we would expect. So if we take a look at what's going on here, we grab the axis index from the box surface index shifted down by 1, and then we grab the positive based on the ANDed value. And so the question is, well, we know that we want the positive and the test against positive to be the same. So we're only going to enter this loop when they're equivalent, right? So what I should be able to do here is say, oh, well, okay, that's pretty straightforward. All I should have to do is create the box surface index in the opposite way, right? I should be able to say, take the axis index, shift it up by 1, and then OR in, you know, the positive value, right? That's the thing that tells me whether the thing is positive along this axis. I should be able to just OR in that value. You know, I can even be 100% explicit here. If the axis index is greater than 0, then it should be 1. Otherwise, it should be 0, right? Then the box surface index is just whatever the axis index was shifted up by 1, ORed in with the positive value, and off we go, right? So I should be able to make that work. Let's start with that. There we go. And so now we should be able to flatten this out like I had it. So I'm not sure what I must have messed up this part down here or something. I'm not exactly sure what I did there wrong. I maybe messed up the calculation of box surface index. Not really sure. So anyway, we can just come through here now. Let me double check this. Let me see if what happens when I do this. No, that's still okay. So I'm not sure what, I must have had a typo in there. But anyway, so we can now loop over the axes directly. So we just do the 3 different axes and then do the positive test based on whatever the ray direction is. And then we can go ahead and compute the rest of the stuff based on those values. So now we're not even doing that if anymore. We're just directly pulling the values out. All right. So let's keep going now and continue to think more about what's happening here. So there's a couple of pieces of information that we know now. So one of the things that we know now that we didn't know before is the normal is always going to be it's always going to look like a 0, 1, 0, 0, 0, 1, 0, 0, negative 1. So there's only ever going to be one element of the normal that actually is filled, right? And that's pretty important because the fact that we know that only one element of the normal is ever filled kind of lets us know that a bunch of the work that we're going to be doing down here is probably easy to simplify in a lot of ways. So for example, let's take ray source n. The inner product of the ray direction and the normal, we know that the normal can only have one component, right? And if we take a look at all the places that the normal is used here, let's see where it's being used. We've got here and here. And that's it, right? We don't use the normal anywhere else. So what we can see is this, these two pieces of information. And in fact, I can reorganize this slightly here with no particular cost. If we take a look at what's going on here, you can see that the ray source direction, the ray source n and the D value are both doing full inner products for no reason. Because all these two things are going to do is they're going to pick out, based on an axis index and positive, they're going to pick out and then optionally negate one of the elements of these two vectors, right? So RayD and rel origin are both just getting extracted. They're not really, you don't have to do any of the multiplies, but that one. And it doesn't really have to be a multiply, it's just a sign flip, right? So what we can do is we can take a look at what's happening here. We can loft this stuff up a little bit, right? And say these pieces of information should be able to get computed in that way. So for starters, let's take ray source n, right? And let's just go in here and put in what ray source n would be. So in both these cases, it's the ray direction which we know, inner producted by the n, which we know right after this line, right? And so if we're going to, and similarly, we've kind of got a couple situations here that are a little bit more confusing, but if you take a look at what happens here with the min corner plus the span, this can be computed a little bit earlier as well, right? So the span and the p value, we could have put those right here, right? Because all they require is that. So again, the d value, the relative origin can be computed immediately thereafter, and that means the d value can also be computed inside here as well, right? Now again, I haven't done anything, right? I just reorganized the code, the order in which the code was happening. So when we run this, we should get exactly the same result as we got before, and we do, right? So off we go. So now what we want to do is we just want to go, okay, let's change these because we really don't need to do inner products here. There's no point to it, right? It doesn't really do anything for us. So what we can do instead is say, all right, this computation for D, this inner product, we know that the normal's value is 1, right? We know that that's what it's going to be. And we know that it's going to be in this axis index location, right? We know that's the element. Now the other two elements are going to be 0. So the inner product of anything with n is really just going to pick out that value. Does that make sense? So all we're really doing is this. Does that make sense? And similarly, down here, all we're really doing is the same operation but negated. That's it. So that's all the normal really does for us in this whole routine. We don't ever really need to compute with it because we're just picking out a very simple piece of information from it. And you can see that our lighting is exactly the same as it was before. So what that means is the normal as a value just isn't even relevant anymore, right? We don't even care about it. It doesn't even factor into this routine in any way. That's all we've got, right? Very, very straightforward. So furthermore, what we can do here is just have a sign value and do these with a multiply if we wanted to, and then we wouldn't even have two branches here either. Oh, whoops. You know what? This is not quite true. These do have to be done after here. Because min corner, max corner still has to do its thing. That's weird that that worked. Like that lighting was still pretty much right visually looking. Even though this has an incorrect displacement of the position of the face. I guess because if move them, yeah, that's interesting, right? This is supposed to be modified first. Well, I'll fix that in a second. All I was going to say is all we really need here is a sign value, right? So we just need a sign value that's going to be 1.0 or negative 1.0, right? That's all we really needed. And then these pieces of information can be computed down here. Like so. So they don't really need to be predicated. They can just be handled directly. So it's really just a sign value there. So anyway, that allows us to fix the bug which I introduced there. It's interesting how much you can get away with and still have a visually correct looking result. I'm sure it would have shown up in other places, but you know. So anyway, point being, all we really need is that sign value, and then we can continue going here. So let's start taking a look at some of the other things that we can be doing that we're not doing yet. So this positive value here we needed to know because we need to know whether we do the min corner max corner thing, and similarly that's where we get our sign from. But we've got our sort of our other stuff here, which is our x-axis, y-axis stuff. Let's see, let's put that down there. We don't need that for anything, right? Yeah. There we go. So similarly here we've got sin x. We don't really need to be doing a test on that because we already have a sign value. The sign value is exactly this, right? It's 1.0 or negative 1.0 based on the positive value, so we can just do that, right? And then we can switch it the way we were switching it before. So that's also, I suppose, something that doesn't really need to be predicated either, right? So again, getting back towards running as fast as we were before and not storing any of that information. So let's go ahead and again, continue forwards with what we're doing. So now if we take a look at what we're doing, a lot of this work to create these axes, I guess one question is, do we really need to do it? You know? And what you can see here is we don't really care which direction the axes go, right? We don't care. So getting the sign right on the axis, which is something we're doing a lot, isn't really necessary because we don't care which way it went. We're checking for essentially an absolute value here, right? We're looking to see whether it's in between the same thing on either side. So if what we're doing is checking for an absolute value, then the x check and the y check values, really, we don't care what the sign of the x-axis even is. So when we do this sin x thing, it doesn't matter, right? It just doesn't matter which one this was. So we can just replace this instead with this. And it would be exactly the same. Right? So we don't need that piece of information at all. We can just get rid of it. And again, eliminate a lot of the work that we're doing there. So now the question is, well, how far can we take that, right? I mean, what else can we do here? So the first thing to note is we already had a way of handling here the fact that we didn't really need the half width either. So we could also say, well, probably the better way to do this would be to return to what we were doing before, where we just multiply these values by 2, right? And then use the width and height. That's what we were originally doing. So now that we see that the width and height is actually what we have, we can also get rid of that. Right? So continuing on, just simplifying these things down. But again, having to multiply by 2 is kind of annoying here, so it probably would have been nice to not have to do that either. Maybe we can get rid of that as well. Like, we'll find out, right? So let's keep going down exactly the same path. So if we take a look at what's happening here, the same logic applies to our inner product that applied to the one with the normal. This ray position thing here is really just getting selected by the x-axis or the y-axis. And what we can see is the x-axis and the y-axis are really just used to pull out pieces of information. They're not really used for a full dot product because we know they're always axis aligned. And a dot product that's axis aligned and unit just plucks out a value. So now we know the sign never changes, so we know that these are just selections. So really what we could do is, again, we can just say, hey, also this can be computed down here, right? So we can just say, hey, why not just take the values out directly that are the values that we want? And so what I can do is say, all right, the x-axis was predicated on this. So what it was saying was, if the x-axis was 0, if the axis was 0, then the x-axis is that. Otherwise, the x-axis is this. That's what we were saying. So what we could do instead is just say, well, all right, if that's what the x-axis is, can we just go ahead and predicate these directly on that instead of doing a bunch of fussing to make that happen? And the answer is hopefully yes. So here we could just say, all right, well, the width then is just the span's x-axis, right? But we don't want its sign. That's all it is, right? Similarly here, it would just be the y-axis. So again, converting that back, it's just this. So there's that width. And of course, we can do the exact same thing for the height, right? Where'd my... Oh, I'm like, where'd my axis check go? It's right here. So the exact same thing we can do for the height. There's my axis index. So I want to pick out the y value in the case where the axis is 2. And I want to pick out the z value in the case where the axis is not. So that's all I really need to do there to get my width and my height, right? That gives me that value directly. And similarly, in my x check and y check, I just need to be able to do the same thing with the ray position. And so, again, I can just say the exact same thing. The only difference is it's going to come from the ray p instead of the span. Right? Pretty straightforward. I guess I should keep this probably rolled out because it's doing the exact same check, but I'm just going to leave that for a second instead. There we go. So again, inner products, not necessary in this case. We're just sort of getting the value out directly if we want to. But again, we're sort of a little bit sloppy here. Like we maybe could do better than this. We'll have to see in a second, just in terms of how we're organizing all of our information. But again, we should still get the same result here, hopefully, with no issues, and we do, so that's good. There we go. And so if we just keep pressing this and, again, we keep sort of wringing it out more and more, you can see kind of how we're continuing to go down. So, and we don't need that anymore. So there's still more we can do here. Obviously, looking at sort of the way that we're computing this stuff with the min corner and max corner and all that, and the sign and so on. So in terms of the sign, in terms of the span, what you can see here is that the place that we use the span is for two pieces of information. We use it for the width and height, right? But, and so we're subtracting these two things in order to figure out that test. But if you think about it, we really don't need to do all of that work, because that work is just, we already know the bounds of the x and the y. They're exactly the min and max corner, right? So we could, the way that we're doing this relative to the box here, we could instead have just had the min and max corner be relative to the position and go from there. I have to look here. I guess what I'm trying to say is the relative origin, right, where we subtract the ray origin minus p there. It gives us an intersection that is centered around the box's position. But it doesn't have to be centered around the box's position, I guess is the way I would say it. We can do this computation relative to any point on the plane. So what we could choose to do instead is just do this relative to the min corner. Because take a look at what happens here. P is a totally arbitrary choice of a point on the plane. And there is no place where we actually use it other than as that point on the plane, right? So we could just say, don't bother with the span addition here at all, and this would still be the exact same set of equations. Because as long as we pick any point on the plane, we're done, right? The only difference is, now when we check, our coordinates for the bounds check are going to be different. But hey, guess what? One of the really nice things about this is now, instead of negative width to width, it's just 0 on one side. It's as long as it's higher than 0, right, on one side, and less than or equal to the width on the other side. So that means we no longer have to multiply, we would no longer have to check against, we do a subtraction on the other side to do that check. Now the only question I have there is, if I shift it to the min corner and I do the intersection, it should just be regular width that I'm testing still as well. Yeah, I think that's fine. But the negative width and height on either side, this should just, you should just not have to multiply by 2 anymore, right? Because you're just taking whatever it is, it should be between 0 and the width. That's it, right? Yeah, I mean, I think that basically just works for the exact same equations. Or not. It should have relative origin Dre-Orris minus P. The x check is no longer multiplied by 2 if it's greater than 0 or less than the height. So I guess the problem there is the sign does matter at that point. So if the sign of the axis is wrong, so I really do have to kind of do this as the bounds check the way that I originally was sort of going to finish doing it. So I guess I can just finish doing it, hopefully. All right. So let me explain that. Oops. So doing it around the center allows me to not care which direction the axis goes. If I wanted to do it the other way, I would have to care which direction the axis goes, and that's why that change didn't work. But let me explain to you what I wanted to be doing as the next step, because it wouldn't depend on that exactly. And then we'll see how we can get there. So what I wanted to do was, when you do the raycast, you're going to get a point, right? And right now what I'm doing is I'm taking whatever we're calling the min corner here. I'm taking that and saying, well, okay, I'm going to displace that and make a point value here. Then the axes are pointing whatever direction they are. Like maybe they're left-handed, maybe they're right-handed, we don't know. They're whatever they are, because we don't want to actually spend the time to generate one facing a particular direction. So they're pointing either in one of these directions, right? We've got one pointing up or down and one pointing left or right. We don't know which. But then we can test against positive or negative width, and we're fine, because at that point we just kind of know that whichever way the axis was going, we're checking for either side of the axis anyway, so it's fine. The problem is this causes us to have to do extra work to create like this p-value and so on. And so at that point, it is just it's a little bit of extra work that we probably shouldn't have to do. But what I was going to say is, well, with the min corner, max corner, we already know how to test the bounds of this thing anyway. So do we really need to do that work? Because we already know what the bounds are, even just in world space, right? But what I'm thinking now is, well, okay, but when we store these boxes, we could have just stored the boxes in the other way anyway, right? We could just store the boxes as a p plus a radius instead of having to do a min corner. And if we just stored them that way, then this would be a non-issue, right? We'd read the p out, and the span would already be what we would know just ahead of time, right? So instead, what we could do is say, like, oh, okay, if we imagined doing this, it's the same thing, right? It doesn't matter which those we do. If we imagine doing this, then we could just say, well, how did I make that same mistake again? Is there something weird about doing it the way that I'm doing it here? I must be missing something subtle. Oh, no, there's some... There we go. So I must be missing something subtle here, because you should be able to do... Oh. Slow day, huh? Gotta make sure you actually put that in parentheses. That's great. So I can flip the meaning of these two things around, right? And if I did that, then I wouldn't have to actually compute these values, right? Because I could just store the box as these two pieces of information, that p-value and the span value, right? And then I can just check these in this way. I can also just do absolute value here, which would be a direct operation I can do on the floating point file. It's just knocking out the high bit. So I can do that in one check, right? I could do something like if absolute value is less than or equal to width, right? I just don't know how that's going to pan out speed-wise here. It's a good question, actually. Let's go ahead and just double-check to see, just vaguely. So, you know, we're somewhere around the 52. Well, okay. So depending on where that guy hops, we kind of need him to stop hopping, I suppose. Let's go ahead and make a more stable test case here. So I'm going to go into world mode, and when we do the snake, So here is us running, and it's around 26 milliseconds, I believe, at stable. Yeah. So I'm just curious to know if this has any effect on it at all. So if I was to do absolute value, absolute value, about the same. About the same. So I'm going to leave it like that because it's a little bit more concise. It didn't really introduce any deleterious effects there. So yeah, if we take a look at what's going on here, what we want to do is again continue to sort of collapse this stuff down into something that's as concise as we can possibly make it. So this information here is all this information could just have been stored directly. And one of the interesting parts about that is if we take a look at the work we're doing here, min corner, max corner are only used for that value, right? So what we could do is just store the boxes that way, and then we'd never have to do this sort of fairly laborious access information check here, which is probably pretty costly. So if we go ahead and did that, let's just see how that would affect things. I'm going to go into platform, and I'm going to take that lighting box thing. And let's just say we've got a P and a radius. That's just how we're going to store it from now on instead. So in here where we've got sort of the span value where we pick out this 0.5, instead we're not going to multiply by 0.5, we're just going to pick the span out directly from that box radius, like so, and the p-value is just going to be the box p-value, like so, and then the min corner and max corner, oops, they're just not going to get used. Right? So all we have to do now is when we actually produce these pieces of information, instead of doing min corner, max corner, we can just compute these values, which we do anyway, right, in here. And this is not the slow part of things, so really whatever we do here is fine for the moment. So all we have to do, oops, is subtract the min corner and the max corner to get the radius, and to get the p-value, which is the center value of them in general, we just have to find the midpoint. Right? So that's the center of the cube and the radius of the cube, and that's all there is to it. So once we have that, now everyone who's doing the get box surface stuff, right, has to switch over to doing it the other way. They have to pass the p and the radius, and that's fine. Okay. But the get box surface call has to be fixed now. I went to the wrong place. To take the p-value and the radius. So now we can look and see, like, okay, so get box surface, it doesn't really need to do this part anymore because min corner and max corner aren't relevant, obviously, right? Oh, you know what? That's not entirely true, though. So it does still need to do that test. I was a little bit aggressive there. It does still need to pick out the correct value of that. Let me just go back and double check that. Just want to make sure we know where how p is being used in that. I think I may be wrong about that. Yeah. So the problem with that is that's not entirely true. For the span, it is true. For the box P, the problem is we still do need to do one piece of work, which is to move it to the place where it was going to go, right? So for the p-value, whichever axis index we're on, we still do have to do one piece of work, which is whichever element that we're on, we have to add that piece of the span in, right? So if we're going the positive x-axis, we have to move p to wherever the face of the cube is that we're actually working on, is all I was trying to say there, right? Okay. So yeah. So this routine here, now we can sort of make all of this work with that as well, with p and the radius. So if we take a look at what we're actually computing here, the span we don't really care about anymore. The width and height of the cube we don't care about anymore either, right? Because all we really need to do is take the radius here, and this produces the half width and the half height directly. Same again is true of p. So the p-value just directly gets added to p there. So really all we have to do is exactly what I was suggesting we do here, right? And we can change that routine to also working off of sine, so it's a little bit more efficient than it was. Yeah, that was basically going to say we're going to end up with a black screen here because I made too many changes at once, which again I specifically said not to do, but then of course I went ahead and did it. So we have to kind of go through now and validate all the stuff, but you know, that's the price you pay for doing that. All right. So if it's positive, the p-value, again, is just going to be equal to whatever the center of the box actually was. And then we're going to either move to the, we're going to move forward along the normal in that direction, right? The other way we could state this, actually, and maybe this is cleaner because in this routine we don't really care. Well, I'll just leave it this way. So we're just going to, in there we're just saying, okay, the radius element, we're going to go ahead and how should I say this? We are going to move from the center of the box to the center of the face by adding however far we have to go radius-wise in that direction. I also want to, hold on a second, let me want to make sure this is being done correctly too, yeah. Yeah, so this is also a 0.5. So I messed that up. The radius of the box is only half of the dimension of the box, right? Obviously, that's what makes it a radius and not a diameter, effectively, of the box. So sorry, that was a mistake. So anyway, this should again all be fine. So once we have our radius value passed into us directly, we should be able to take the half width and half height very trivially. Like all we have to do is just say, okay, let's inner product them with the x-axis and off we go, right? And that information is now available to anyone who wants to use it, I think. So I feel like that's roughly correct. And then going back to the raycast, just to make sure, and then we'll go debug this. In here, again, all we're doing is saying, well, whichever direction we're going, we're compute a sine value. The span is just going to be the box radius, right? And so let's go ahead and change that to be radius. And so what we're going to say is, all right, we need to go in whatever direction. If we're negative normal, we need to go down or up if we're positive normal, right? So whichever positive or negative we're testing, we need to move on that axis. We need to move from the center of the box up to the face or down to the face. Then all of this stuff is the same as it was. This didn't change at all. And then when we pick out values of the span here, this is going to give us the half width, right? Oops. And one of the things that you can see here is the X check and the Y check here. I don't know why we're even still doing absolute values on these, because we're doing an absolute value of them down here already. So I guess what we could say here is, first of all, we know that the radius itself is always going to be positive in that way. So this really shouldn't have to be an absolute value at all, right? Oops. And this shouldn't have to be an absolute value because we're doing the absolute value down there. So why we have that, I don't know. Just me failing to notice it at the time when I typed it in. So yeah, really all this has to do is pick out one of these two things right here. Same with here, right? And these are just picking out those radius and ray-p values. And then we do the absolute value on the check because we don't really know what that is. But the half with the half-width, they should always be positive anyway. So I think that's all of that information that even needs to really happen here, if that makes sense. All right, so now we got to figure out why this is going wrong, right? Like, why are we getting a black screen? And I'm not really 100% sure how we ended up with that. So something busted is happening here. We just don't know what it is. So now we have to figure out, yeah, is it something in here that we did in switching to it? My guess is, you know, probably not. I don't really know, but probably not, because we should just be seeing we would be seeing erroneous lighting, but we'd be seeing lighting just the same. So my suspicion is I messed up the box, get box surface call, right? So in here, when I changed to be using the p-value instead and the radius instead of using the min corner and the max corner, my suspicion is that I messed that up, not that I messed up the raycast routine. Again, don't really know that that's true, but that's just my rough guess of probably who got screwed up here, right? Okay. So let's go ahead and, oops, I meant to do that rebuild on debug. So let's go ahead and rebuild debug here, and let me run the program, make sure it's all good. And let's just validate our getBox surface call, revalidate our getBox surface call. So I'm going to go ahead and start inspecting this. So what we get here is we get a p-value and a radius value, and then we need to see what the axis index and the positive value are and the result. So taking a look at these, the p-value that comes in, you know, doesn't get changed. It should. It's supposed to. I mean, correct me if I'm wrong, but those are exactly the same. So the axis index here is 0. So this operation should have taken place, right? this should have been added, and it wasn't? All right, so I don't pretend to know why that happened, so let's take a look at that in detail. Oh, no, okay, right. This is initially past it. No. So that was correct. I'm sorry. Yeah, I was looking at the wrong thing there. So here's the radius value. For starters, the radius is negative, so that's just wrong. So I'm going to take a step out and see. I must have done the subtraction incorrectly there in the thing that passes in the box surface. So that's a obvious mistake and would obviously account for the black screen. So that, needs to get fixed immediately. Oops. Okay, so in here where we have our subtraction, yeah, this is supposed to be max corner. Let's make this a little bit more consistent. So we'll do max corner, min corner. There we go. Okay. So let's try that again. Our radius is now positive. That's exactly what we want. Half width, half height. All right. Normal. It's -1. Okay, much better. All right, so that's looking better now. Let's see what our visuals look like here. Okay, so we're back. So it looks like it was just that I had accidentally set the radiuses to negative. So that was a bit of a mistake there. Let's go ahead and change this back to 02 and see where we're at. Okay. All right, so again, continuing to get better. Pretty nice and smooth there. We can go back in now and add our little friend, just to increase the number of light things bouncing around. Here we go. And so I think we're now actually also getting in the range of what we were originally running at. I think we're fairly close. I don't remember exactly where we are, because again, I'm not really in an optimization mode right now. I'm kind of more just in a let's make this algorithmically relatively correct first. Because we need to use boxes one way or the other. So again, pretty good, right? Not too shabby so far. So now, again, let's just take a look at that raycast again and see where we're at in terms of simplification of it. So yeah, looking here at what we've got, I mean, this is pretty drastically simplified from where it was. Box surface index is kind of something that's annoying to have to compute here, because it's really only used for this readout. But yeah, hard to say. I'm going to go ahead and turn off this timed function, by the way, because that's actually taking some time in there. I want to see how we're doing without it. Quite a bit better, actually. Right. So I think we're back down to roughly where we were before, right? I think we're getting right. We're in better shape than, probably even better shape than we were in before, potentially. So yeah, this is looking pretty good. It's possible, I don't actually know, but it's possible that the fact that this is still in a for loop and this can't be optimized is pretty bad, right? So I am tempted as well to sort of macroize this a little bit and just actually do this check unrolled, if that makes sense. So, I don't necessarily think that's a great idea, but I am curious about it. So I'm just, because we only have 5 minutes left, I'm just going to do that because I just want to see. So here's what would happen if we were to unroll it. So if it were the x-axis, then, you know, it's just x. And we pretty much know exactly what those values are. Makes sense. E-axis index is just always x in all of these, like so. And yeah, all of this stuff, we know that the axis index is equal to 0, so it's just Ray P, y and radius y, and then the axis index equals 2 is not true. So we know we do those two. And that's pretty much it, right? That's just all we need to do there. For the y-axis, oops, didn't mean to do that. We know that this is just going to be 2, because that's what 1 shifted up by 1 is. And then, again, the rest of this stuff just becomes y-axes. We know the axis is not equal to 0. So it's that. And we know that it's also not equal to 2. So it's that. And off we go. And finally, the z-axis. Again, what we're going to be shifting up here is 2. So that's going to become equal to 4, right? If I'm not mistaken. I think. Because it's equal to be 4 or 5, depending on whether positive is 1, 0. So I think that's right. And again, this few places where we actually access that information goes away. It's not 0. It's not snowflake. It is axis 2, so this applies. So let's just see how that goes. I think we did it right, and we'll see. So there's no question that that helped us, I think. Just not a whole lot. So it's not clear that we really would want to do that necessarily off the bat. But you know, you can kind of see how unrolling that loop can simplify things, right? Can definitely simplify things. And, you know, we can start to look at this as being even more simplified if we start to pull out, you know, terms. Maybe we can look at collapsing some of this stuff as well. You know, who knows? We could just take a little closer look here at that part, like so. So here's another example. So ray source n doesn't depend on anything but the positive or negative sign here. So that's interesting. Well, I guess that doesn't really matter. Yeah, there's significantly more we can do here, I guess is all I can say. We can keep looking at this. But yeah, there's definitely more we can do here. So also, if we take a look at what happens here, so the x check becoming ray p.x, radius x, that is actually common for these two. So that can be switched here, and similarly these can be switched here. Oop, that was not. I went too far. That's not what I meant to do. I meant to switch the other half. There we go. What I meant was these. Right? So if I go ahead and pull out these, there's really not much point in what I'm doing right now. I just wanted to kind of mentally have a feel for what is actually happening in the routine as it flows down. So this will not really improve the speed, but it's just something to kind of be aware of. So you can see it starts at YZ. It doesn't really change here. So this changes, the other one doesn't change. And then similarly, the same is true here. So only the half height changes here, right? So I'm just kind of looking at the way that flows through the code. Yeah, it's just worth noting. Oh, you know what? And this is not actually true. This does have to be redone every time. So I think that's still substantively the exact same thing. And so again, looking at this, I just think there's still a fair bit of slop in here that we could optimize away. We have to think it through a little bit more, but I'm pretty sure that we're not done getting rid of a lot of this information. One thing that's interesting here is ray source n and d. If you take a look at where that's being used, so ray source n is only used once, and d is only used once as well, I want to say. So unless I'm mistaken, this multiplication by the sign is just irrelevant, right? Like, it just isn't necessary, I don't think. Because we're multiplying two things by the sign, but those things just get divided. So I think you can even get rid of that multiplication entirely. Since no one cares what the sign of those two things are. So again, still kind of just an arbitrary, an arbitrary sort of aspect of the math that just kind of falls out. We just really don't need to do it. So yeah, keeping going along that line of reasoning, what you can see here is now sign is only used in one place, right? So in a sense, the only reason we even need to know whether we're the positive or the negative anymore is strictly because we need to have an opinion about how to displace the point. So that's really it. It'd be nice if we could get rid of that because that's the only reason we need to compute that, but I think we have to, unfortunately. So anyway, that's just kind of nice. And this is starting to look relatively respectable, within reason. All right, I'm going to go ahead and go to Q&A. But what I can also do now is I can also switch back here to this version of the routine and make that same optimization, because that's true regardless of whether it's unrolled. So for example, in here where I do the sign multiplication, that's just not necessary anymore, right? Because that piece of information is never used. D and racehorse n are only ever used in that context. That's the only place they're actually used. So you could even just get rid of them, right? It's just that. Oops. That. And no one ever needs to do that particular operation with the sign. So that's a pretty meaningful speed savings even just there, because it just eliminates multiplies that were completely superfluous and not unnecessary. Let's see. That did not work. There it goes. All right. Gprincip, is the lighting done after this? After what? The lighting is not even close to done. We've got several more things we have to do to it. You may now sort the episode guide entries from new to old. Oh, really? Oh. Oh, check that out. That's pretty sweet. That's cool, Miblo. Stuck Panda. Which headers do you include for working with OpenGL? We included gl.h, I think. How long until you'll move all of this to the GPU? I don't know. I also don't know for sure that we will. So one of the things is once we do it multi-res, if we wanted to, we could also just do it on the CPU multi-threaded and probably be fine. So it's going to be an interesting call. When we're done with it, we'll have to see just how likely we think it is to be able to run efficiently on the GPU versus the CPU. So it's hard to say, right? because it would get 4 times faster than it is right now if we ran it multi-threaded, probably. Well, that's not really true. But let's put it this way. If we SIMD optimized it and multi-threaded it, it would be massively faster than it is right now, probably. And so, you know, we could be looking at a pretty dramatic speed up, right, from where it is right now on the CPU. And then plus with multi-res, it would scale really well and so on. So it's possible, that we could prefer doing it on the CPU because the CPU is just faster at random access kinds of things like ray tracing. If traversal is a big deal. But it might also not be. I don't know. So who knows? Why did inlining getbox to raycast result in such an improvement? Without looking at the generated assembly, we don't know exactly why. But the general case is because the compiler doesn't have that much logic in it, right? It's running in a fairly short amount of time. It doesn't spend, like, you know, what does it take, 4 seconds to build the game? It just doesn't spend a lot of time thinking about how to optimize the code. I know we think of optimizing compilers as being pretty advanced or something, but they're actually really primitive, especially ones that run in line like this. So it's got a bunch of heuristics that it uses to determine how much of an improvement it's going to get if it inlines something. It depends on compiler switches. Like maybe we could set some compiler switches to tell it be more aggressive with inlining than it would, right? Et cetera, et cetera. And so, you know, when you start stacking things on top, like, oh, you'd have to inline this, and then you'd have to realize that once you inlined it, you could get rid of this array access because now you know what it is, and you could unroll a loop, and blah, 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 right? The number of steps you're requiring the compiler to take before it gets to code that's fast just reduces the chances that it figures out it should do that thing, you know? And so when you have a particular like thing that actually needs to be fast, you typically have to massage it pretty well to get it into a place where the compiler really knows exactly what it should do. It doesn't have to think too hard. That's all. Will the lighting boxes remain sort of separate from the rest of the render commands flow? Yes. They will just be pushed on in a separate stream. Great stream, by the way, and the lighting looks great. The lighting is going to look insanely good once we actually start using it. Right now, we're not even, right? Like, right now, we're doing the worst possible thing, which is we're just lighting individual surfaces, but we actually have interpolation capability in there now. So once I actually peg light samples for interpolation across the faces of surfaces more, it's going to look a lot better. So it will improve dramatically. We'll get there. You'll see. In my engine, I have 3D models that contain a buffer of uint8, which is cast into a struct which contains OpenGL handles for the model. My instinct is to hide the OpenGL stuff from the game engine itself. Is this a good idea, or should I just give it into the OpenGL overlords and put pound include GL in my game code? Maybe I'm just being dogmatic. I would never put pound include GL in your game code. Because you might want to port the game to something that's not GL, and now you've got to deal with that, right? So I always say platform doesn't go in the game code, right? Sometimes you have to inline certain platform things into the game code, like SIMD, for example. You may have to have like things that switch on it, but you still want to make sure that it's not actually ever touched by the game code. So it's less about whether you pound include gl.h in the game code or not. It's whether the game code ever refers to anything in there. If the game code is ever going to actually be using gl.h somehow, it has to be doing it through some opaque thing where it doesn't actually rely on that, so that if you were trying to port to Vulkan, Direct3D, whatever, PlayStation 4, Xbox One, blah, 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 Nintendo Switch, you would always be able to use a different graphics layer and the game code doesn't have to change. That's the important part, right? Skyvault Games, when the JAI programming language stabilizes, will you be considering using it for future Handmade projects? Of course. Yes, definitely. I don't know what the situation will be like, or when I would have a chance to really start to learn it and move over to it in any serious way, but obviously I will be considering it because C++ is a giant steaming pile of dog turd. So I would greatly welcome the possibility of programming a language designed by people who I think are more sane, right? Is there an episode that explains some generalities about what OpenGL shaders are? Yes, there are some episodes about that. If you go to the annotated episode guide here, and put in shader, you would probably get some information about that. So let's see. This is probably something that might be worth listening to start with. Here is one where we actually implement compiling and linking shaders. So maybe starting on day 368 would be good. Introduction to vertex and fragment shaders on day 369. That sounds pretty good, right? All right. No more Q colons. So I will wrap it up. All right. Thank you, everyone, for joining me for another episode of Handmade Hero. It's been a pleasure coding with you, as always. If you would like to follow along the series, you can always pre-order the game on handmadehero.org, and it comes with the source code, so you can play around with it. If you would like to catch up on past episodes, we do have an episode guide that I was just showing, and it's a great place to do that if you missed old stuff. We have a schedule bot that says when we're going to be live if you want to catch a stream. We also have a contribution page if you want to contribute to things like the episode guide, which are made by people in the community, and so we try to funnel money to them to support their work. That's a good place to check that out. That's about it for today. I will be back next week when we will continue to optimize our lighting code. At this point, our raycast is probably good enough for now. We probably don't need to spend a lot of time optimizing it. There's a lot more we could be doing, but we're probably not going to do that, because the more important optimization, which is the one that I want to get to first, before we go any further, is starting to deal with things multi-resolution. And that's just so we can scale the lighting. So what we're going to do next week is we're going to go ahead and blow out the scene to some huge number of entities and lights and everything. And then we're going to start focusing on methods that will allow us to still light those scenes without tanking our performance. So that's what I'll be doing. Hopefully see everyone here for that next week. Until then, have fun programming, and I'll see everyone on the internet. Take it easy, everybody.